Hi everyone, so here we are again. Coming to you today is the second half of the lesson 4.1 that we began yesterday. So if you have your handout out, we'll pick up where we left off. So if you remember what we did yesterday, we introduced the idea of what an antiderivative is, and how what you were really finding in your homework last night, because all of them had the plus C constant of integration amended onto your answer, they were referred to as general solutions. So that kind of leads into what we're talking about today. Here we go. All right, because you might remember me mentioning yesterday that when you find an antiderivative and we attach that plus C at the end, it's really to acknowledge the fact that there could have been a number at the end of that antiderivative equation expression that you found, that when you take the derivative of that number, the number of course goes away. Right? So that's what that's really there to acknowledge. So what ends up being created is, and this is the part you hopefully remember from yesterday, is a family of functions. And that's what you see in this graph here. If you can read the little fine print down there underneath the graphs that you're looking at, this is the particular solution that satisfies the condition of the fact that f of 2 is 4 when the function is x cubed minus x minus 2. So really what this accounts for is you're really going to be given initial conditions that will enable you to find what the plus C value is. All right, and that's kind of what you're looking at here. These all are the same antiderivative, but with different C values. All right, if you take a look at the very, very top up here, you can see there's like a C plus 4, C plus 3, C plus 2. But notice they're all the same shape. They're essentially all the same equation, expression. What really varies is the constant, which we know from algebra is going to dictate the placement, the vertical placement of the curve in the plane. Okay, so once you're able to find that plus C value based upon conditions that you're given, what you then have is a particular solution, and that's what we're talking about today. So the easiest way to do this, of course, is to just dive into the practice problems. You'll notice there's not a lot of them, so I don't anticipate this will be too long of your time on your snow day. So if you take a look at the first one, we're finding the general solution of capital F prime of x equals e to the x, and we're asked to find a particular solution given that f of 0 equals 3. So if you think about like the notation and all we had yesterday, capital F, remember, was the antiderivative. So basically what we're doing is the antiderivative of e to the x because we want to do the derivative of it. Okay, so we're going to set it on up. So what we're finding is the original function. There we go. Is going to be the antiderivative of e to the x dx. All right, hopefully you remember what this rule is. Antiderivative of e to the x, remember, is simply e to the x, all right, plus c. All right, so we know that's what the original function would have been. So we want to find the plus c part. Well, we're given the fact that f of 0 equals 3. So we're simply, remember, this is your x. We're simply going to put that in place of our x. Remember, e to the 0 is 1. So we get 2 for our c value. So really what that tells us is our real function in the end is e to the x plus 2 specifically. All right, and that's what we refer to as a particular solution that we're able to obtain thanks to the specific information we're given. Because what we're given in that f of 0 equals 3 is one particular point that we know has to be on that curve in the end. So we're really just making use of that information to enable us to find the c part. And that's what a typical one looks like. You'll find they're pretty much all done the same way. So what I have here are just a few different problems of, different ways you might see things worded, but I think you're going to find when we actually do the problems, they all have the same feel to them. All right, so in number 11, at any point x comma y on a particular curve, the tangent line has a slope of 4x minus 5. And if the curve, the original curve, contains the point 3 comma 7, find its equation. Well, think about the slope that you're given. So we know our slope is 4x minus 5. Well, geez, slope of a line tangent to a curve is our definition of the derivative. And thanks to what we talked about yesterday, we know if we take an antiderivative of a derivative, those things cancel each other out, and that's how we can get back to the original equation. So really what we can do is we're going to be able to find the original function by doing the antiderivative, really, of the derivative. All right, I'm writing everything out very, very formally here. So what we're taking the antiderivative of is 4x minus 5. That's a lot like what you did last night in your homework. All right, so I know you know how to do that. We'll kind of go through all the steps. So we'll keep the 4 as the coefficient, and we know antiderivative of x is going to be x squared over 2. This is going to be minus 5 plus c. So we get 2x squared minus 5 plus c. So that's our function. All right, so that would be the general solution, all right, if we were to leave it like that. All right, but we know that the point 3 comma 7 is on the curve. All right, so really we know f of 3 is equal to 7, so we can put 3 in place of our x, so 2 times 3 squared is going to be 9, minus 5, plus c, I'm running out of room. So let's see, 18 minus 5, that's 13. 7 minus 13. I think I forgot an x somewhere. Oh, you're probably wondering, I did forget an x. That's what the pause was for. I'm like, I forgot an x somewhere because I knew this is a 15. This is why I always do my notes. So if you were just thinking, isn't that supposed to be an x, Miss Henderson? Yes, you are correct. So hopefully you were thinking that. I forgot it when I did the antiderivative of 5. So, okay. Now that makes more sense. Okay, so now we have 18 minus 15, that's 3. So c is 4. All right, so now we've been able to solve for that particular c value and find our particular solution. So what we end up with for the actual function is 2x squared minus 5x plus 4. And just like we were talking about yesterday, you can still check your answers. If this is the original function, we know the slope would be given by the derivative. So if we did the derivative, you do get 4x minus 5. So you can still check your answers just like we were talking about yesterday. So we're asked to find the equation for y, given that dy dx is equal to negative 1 over x squared. And the point, you know, 1 comma 3 lies on the curve. So what you see there with that dy dx, this is what a typical, like this part right here, this is what a typical differential equation looks like. All right, that dy dx. You might remember me saying yesterday, a differential equation is really just an equation that's presented to you as being the derivative of something. Okay, so that's what this is. So I'm going to start trying to get you sort of geared towards some of the things that you're going to see later. Okay, so let's start by rewriting that. We can bring the x squared up to the numerator. Okay, And another thing that we often do, and you're going to be doing this a lot later on, is what we refer to as separation of variables. What that means is get all your x's to one side, get your y's on the other. So I'm literally going to multiply both sides by dx. It's sort of like that differential idea that we saw at the end of Unit 3. All right, so I really just multiply both sides of the equation by dx. So now I'm going to go ahead and I'm going to take the antiderivative of both sides. All right, just like you learned a long, long time ago in math, what you do to one side of the equal sign, you have to do to the other. And that's really all you're doing here. All right, now think of it this way. On the left side, that's technically like 1 dy. So when you take the antiderivative of that, remember you're thinking, okay, what do I take the derivative of? And 1 is going to be the answer for the derivative. Well, that's got to be just plain y, because we know the derivative of y is 1. Okay. Now on the other side, we just do the normal power rule like we were talking about yesterday. So I'm just going to leave the -1 there for now. Remember that we're adding 1 to the exponent, and then we're going to be dividing by it. So that's going to be x to the -1 over -1. So I'll just write it all out for you. All right, and then of course plus c. All right, so let's kind of clean it up a little bit. We have a negative times a negative, that makes positive. So really this is just like 1 over x plus c. So that's basically your general solution. Okay, and now we're just going to go ahead and use the fact that we know the point 1, 3 lies on the curve to go ahead and find c. All right, so the y value obviously is 3. We're going to put 1 in place of our x. So 2 is equal to c, obviously. So in the end, our function is 1 over x plus 2. Not so hard. And this would be, of course, your particular solution. So we only have one more, and that's it. So hopefully this is making sense for you. All right, so solve the differential equation. The second derivative of x is equal to x plus square root of x. And notice how you're now given 2 bits of information. You're given f of 1 equals 1, so that's of course pertaining to the original function. You're also told f prime of 1 is equal to 2, of course referring to the derivative, the first derivative. So this is where it's going to be, because think about it, if we want to get back to the original and we're starting at the second derivative, we're going to have to do an antiderivative twice. Because if we start at the second derivative, do an antiderivative once, that's going to get us back to the first derivative. Well, then we'll have to do an antiderivative again to then get back to the original. So this is sort of like a multi-step type of problem, okay? So I'm going to, before I even do anything, I'm going to rewrite that original. You know, just for, you know, visual reasons. Of course, x to the 1/2, okay? All right, so I'm going to kind of number the first, all right, so the first thing I'm going to do is, if I were to take the antiderivative of that second derivative, that's going to give me my first derivative. All right, and this, of course, is an antiderivative. I know you know how to do. So antiderivative of x is going to be x squared over 2. Antiderivative of x to the 1/2, remember you're adding 1 to the exponent, and then you're going to divide by that new exponent, okay? So that gives us x to the 3/2, but then we're dividing by 3/2, so that means we end up multiplying by 2/3. And then, of course, plus c. Okay, so what we could do now is sort of stop and use the information we know to find this particular c. Okay, so let's go ahead and do that next. All right, you just have to make sure you're grabbing the correct information. So we want to use the fact that we know f prime of 1 equals 2. So we can set that derivative, first derivative, equal to 2, and we're going to put 1 in place of our x's. So we got 1/2 plus, that becomes 2/3, plus c. Ooh, fractions, yay. So let's see, 1/2 plus 2/3. So that's, common denominators, that's fun stuff. You can do that on your calculator. I already know what the answer is. It's 5/6. Feel free to do that on your calculator. You probably would want to keep it as a fraction, only because it's definitely more of an exact value as opposed to a decimal, okay? So kind of keep that in mind. When you do get fractions for these, you usually are going to leave them as fractions, okay? So now we know what c is for that, okay? So now we can set it up. Hopefully I want a third step. All right, so we got our first derivative nailed down. So now we can go ahead and find our original finally by taking the antiderivative of that first derivative. So we're doing x squared over 2 plus 2/3 x to the 3/2 and plus 5/6. Because you'll definitely want to put that 5/6 in place of the c. And we're just going to go ahead and find our antiderivative from there. I think I have, there we go, you can see both. That works. All right, so I'm going to leave the 1/2 from that x squared over 2 there for now. Think of it as like a coefficient. So when I add 1 to the exponent and then divide by it, that gives me x cubed over 3. All right, so that's going to become like 1/6 x cubed. All right, the second term, I'm going to leave the 2/3 there for now. Remember, I'm adding 2 over 2 up here, okay? So that gives me for my exponent 5/2, but then I'm dividing by it, so I'm really multiplying by 2/5. Like I said, you get really good at fractions with these. And then the last one is just going to be 5/6, and I'm not going to forget my x this time. And then, of course, we need a plus c there, okay? So let's see, when we kind of do all this out, we get 4 over 15 x to the 5/2. All right, so that's our general solution for the actual original function. All right, so now we can go grab that other bit of information. We know f of 1 is 1. So we can set the function equal to 1 and put 1 in for our x's. So this becomes 1/6, 4/15. I think we'll be doing this in our calculator too. And I'm sure you guys know how to do that. Just do the math and in the end use, what is it, that math to fraction, math in the far left column, to fraction, that will tell you the fraction in the very end. I would highly recommend that. No, you would not ever have to do this without a calculator. So your constant, if you want to give it a try, double check my math, it should be -4 over 15, okay? If you want to check that out and make sure I did it right, okay? So what we have in the end then is our original function really ends up being 1/6 x cubed plus 4/15 x to the 5/2 plus 5/6x minus 4/15. And as we've been talking about, and I encourage you to do so, go ahead and find the second derivative of that. That's not so hard to do. And make sure it matches that x plus x to the 1/2. All right, so as we've been talking about, there's definitely ways you can check these that aren't too difficult. Now, if by chance, just something that you might come across, I don't know if you will, but just in case. Suppose they had given you this problem, and really what they wanted you to find were the general solutions. So they had not given you those conditions that f of 1 equals 1 and f prime of 1 equals 2. All right, so suppose it just said, solve the differential equation f double prime of x equals x plus square root of x, and that's it. What you would need to do as you work through the problem, obviously when you go to find that first derivative, you're going to have a plus c, okay? You would not have any way to find that plus c. You'd have to leave it as just plus c, all right? When you go to do like step 3 down here, in place of this 5, 6, you would have a c, all right? So when you go to find the antiderivative then, all right, instead of having 5, 6x, you're going to have c times x, all right? Because you'd have to remember c is a number. All right, and then for the constant of integration for that original function, you can't pick C again. You have to pick a different letter. So most do D as in dog. Okay, another way to do it is you could do subscripts. So you could do C sub 1 and then C sub 2. Okay, but that just might be something you come across. If you do, don't be alarmed. You will see ones like that someday. But that's how you would handle it. All right, you might need 2 different letters to sort of differentiate, tell the difference between the 2 constants of integration. Okay, so just something to kind of keep in mind. Okay, as I said, most just do C and D. Textbooks will often do like C sub 1, C sub 2. I usually just do C and D because it's easier. So you can really do anything you want. Okay. All right, so for homework, and remember you needed to have emailed me pictures of your homework, okay? If you have not yet done that, remember by 3 o'clock today you can do that, and after 3 o'clock I will be posting the solutions. So what I'd like for you to do for homework tonight is this part over here. All right, you did up to 16 to 28 even yesterday. Let me double check that. Yes, you did. So the rest you can do, and you can see there's not that many. But kindly do those tonight. I guess we'll wait and see what happens tomorrow on Thursday, and maybe I'll be coming to you virtually again. I don't know. So again, just please keep your eye out for your email, okay? But thanks for watching. I'm glad you're home safe and warm, and hopefully you're warm. I hope nobody lost their electricity. Email me if you have any questions. Otherwise, hopefully I'll see you soon.